the assignment that you have to submit today?
Yeah, that Professor Mitro will clarify on that.
Okay, got it.
Okay, so he's handling that assignment. So I will just close on the runtime environment discussions we are having. Okay. Okay. I think let me go back a couple of slides. This is what we have already. Is it visible now? Is the presentation visible?
Yes, sir.
Yes, sir.
Okay. Okay. So we discussed about the function call with int data type. This we have already discussed. So the symbol table for add and main and all that stuff. And after the peephole optimization, we got rid of the temporaries. These are all steps that we will have to do when we actually generate the code. I'll discuss that when we do how to do that. But we are just showing the possible stages and in the code transformation. And then we saw that this code gets generated in the assembly, where in the beginning of the text segment, the layout of the variables are given, which eventually gives us the structure of the activation record. The same for the add function. I'm on slide 24. The three variables have got kind of their address expression. So this is what we can say is equivalent is an offset, which will give me the address expression when we offset it with the extended base pointer. So with that, we got this activation record where 1024. I've just chosen a arbitrary value just for illustration. Is a base pointer where actually the base pointer of main caller will be stored before the control comes to main, and then on this side, on the lower address side, I have -4, -8, -12, 4 byte int each for A, B, and C, the three variables. On the positive side, with respect to the base pointer, we have 4 bytes left for return address. That will have to be, which we are also considering to be of 4 bytes. And then we have the argc and argv, the two parameters. Argc is the int parameter and argv is the pointer parameter. So this is how you decode the offset into the structure of the activation record, as you see. For add, we have the base pointer at 996, which is effectively on top of this, because main is calling the activation record of add. So if you calculate with respect to that, this is 1012 we had as a top of the stack. So the next available position is 1008 after leaving out that 4 bytes. So if you go back 12 bytes from that, because this has to be at +12. So if you go back 12 bytes from here, 996 is your base pointer, activation record base pointer for add, where the base pointer value of its caller, which is main, which is 1024, will be stored. So that is what is being shown. On the lower address side, you have one variable Z having 4 bytes, so it is at 992. On the higher address side, you have return address, which is so here we are assuming here the compiler has taken that the return value is not returned through the stack. It is not returned as a part of the activation record. It is actually being passed through a register. So only the return address is shown, and then you have the two parameters X and Y, which are put in here at 1008 and 1004 and 1008. So this is basically what's going on. These are the registers. So this is a code in execution. If you see, then at the beginning we have all these offsets. I'll just step through a few of the instructions. Rest you can work out yourself. So we have push. So we are assuming that it is ESP is 1028. This value is arbitrary because that depends on where main caller had as a top of the stack. So this is the top of the stack. So you push EBP, which is the base pointer of the caller of the main. Right? So that is the current value of the EBP that you push. It becomes 1024. So on different columns on right, you can see the relevant values of the registers and the stack variables. Then you move ESP to EBP. So EBP now becomes 1024. So that is where you will have your main starting. And then you subtract 12 for these three variables. You fill them up with the all C values. So this is a fill value, as I said, to detect that whether it has been at all been initialized or not. And then you move 2 to this effective address, the address of A, which is EBP plus underscore $, which is EBP minus 4. So it is 1024. So A is at 1020, which gets 2. Similarly, B is at 1016 because B underscore B $ is minus 8. So that gets 3. And then you put that to EAX, push that onto the stack. So EAX gets 3 because you have moved this B onto EAX. You push that, so the stack top becomes 1008. And then you move A onto ECX. So ECX becomes 2, and you push that. So in the activation record of the add, you have already created this actual parameter values. Then you do a call, and the call will naturally reduce the stack pointer by the address size. So it will put the return address here, which is the return address is where you'll get after you have returned from here. So this is the return address which is shown here. Right? So this gets to this value. And so then you are in. So with the call, you have actually come to add. So you add this ESP with 8. I'm sorry, with this you will go to add, and on return you will have this. So on return, what you'll have to do is you'll have to undo the push of the parameters that you had done. So 2 pushes were done. So it was increased to, it had changed from 1012 to 1004. Then call, the return address made it 1000. So when you return here, it is again 1004 because the return address has been removed. And then you add the pushes that you had done. So this is basically equivalent to doing 2 pops. So you add to the stack pointer. So the stack pointer is back to 1012, where you do the remaining protocol to return. In the next slide, in terms of add, When you get to add your value of the stack pointer is 1000, as you have seen. So you push the base pointer of main, the activation record pointer of main, which is 1024. You push that, so stack pointer becomes 996, and on the stack there you have EBP, that the base pointer of main is 1024. You move this stack pointer to the EBP, and that is where the stack activation record of add is pointed to. And then you keep on doing this task. You create the space for, you put to the space for Z, you take X as EAX, add Y to it into EAX, and put EAX to Z, that is X assign Z equal to X plus Y, and then you put it to back to EAX. As you can see, these are not optimized. So you are just doing stages as you should go, because you are again moving it EAX because you are trying to now realize return Z. So return Z by protocol here will return the value in the EAX register. So we are putting Z onto EAX. Then you restore the stack pointer, EBP to ESP, and pop the EBP so that the base pointer of main gets the original value back, and then you return. And you return naturally through indirect addressing, and you are back to main. So this is decoding the assembly. We can get a very clear picture of how the activation record can be laid out. And again, I would reiterate that this is not something which is unique or something which is standardized. It is up to your design. You can make changes, you can do things differently. But certainly this, decoding the assembly gives you a very clear idea of how to handle different, features on the activation record. For example, we are just showing it now for a non-debug, non-optimized build for a function call with only integer types. Now, if you have to make a debug build, or if you make an optimized build, or if you are using types which are other than int, you are say you have a type which is a struct, or you have a type which is array, you will need to design the activation record. So obviously you can do the design in your way, or a good way to get insight into how the activation record can be done for different cases. You can just write a simple short code having that feature and generate the assembly and decode that assembly and see what kind of scheme is being used. So that's the whole idea. So I'll move on next. So what I'm doing here is I'm using the same code, but I have done a debug build, that is a safe, which is called a safe debug build, where I would be using the safe debug feature of the debugger, right? So first, notice the differences. In terms of the offsets of variables, you can now see that the variables still are of the same size 4 because they're int. But the difference in the offset, which was earlier of 4, now has become 12. Right? So this has become 12. So 30 minus 32 plus 12 is 20. Plus 12 is minus 8. And then earlier you had this only, this difference now is 16. Yeah? Earlier it was of 8. Right? So all these changes have happened, whereas on this side things have not changed. So that is what we are decoding, as to understanding what is actually going on and how that can help in terms of the generated code at the runtime. Okay. So again, let's look at the assembly. Push EBP, that remains same. Move ESP to EBP, remains same. Now it is subtracting a very arbitrary number, right? Earlier it was, if I go back, I'm on slide 23. Slide 23. Earlier it was subtracting 12, which is this value, which is understandable. So it has to allocate 12 bytes on the lower side of the address. So it is subtracting 12. So that's quite okay. I'm coming back. I'm back to slide 30 again. And now we see that it is not subtracting 32, which I would have expected by symmetry, but it is subtracting some 228. So what is this magic number 228? So let me decode, and it will become clear in another 2 slides as to the meaning of this decoding. The 228 happens to be 32 plus 4 plus 192. Just remember these figures, 32 plus 4 plus 192. You can write it down on a separate sheet also. Okay, so it has subtracted that part. So what it is saying is this is the space for the activation record beyond the EBP that it wants to reserve. Right? So this is the intention. This subtraction has that intention. The semantics of subtraction is on the higher address side these are the fixed things which are basically interfacing with the caller, because you have the parameters, you have the return address and all that. And on the lower address side, you have your own local information. So for that, you are reserving 228 bytes, right? 32 plus 4 plus 192. Let's see. Now what it does, this piece of the code basically fills up these 228 bytes with this, fill pattern values. Pushing these registers is just to make sure that you do not lose their current values. Right? So what do you do? EDI. In EDI, you are taking EBP minus 228. So wherever the EBP is, EBP minus 228 is a space that you want to reserve, right? That is what you have subtracted, because EBP was same as ESP. Right? So you take that and you move that to EDI, but it is not a move, it is a ALEA. ALEA is load effective address. If I move, then the value stored at that address is moved to the registers. But if I do LEA, load effective address, then not the value, but the address itself is moved to EDI. So EBP minus 228, this is not taken as an address, it is taken as an address value. And that address value is moved to EDI. So that is load effective address. So this is a different instruction. So EDI becomes your EBP minus 228 address. Then you move ECX 57 into ECX. What is the magic of 57? 57 is 228 by 4. Right. So if you have 228 bytes, then you have 57 4-byte words. Right. So because this fill pattern CC is a 4-byte pattern, right? So what you are saying that if I want to fill up all these with CCs, then I need to fill up 57 times with this 4-byte pattern. So you put this into ECX, and then you move this fill pattern into EAX. And then you do a repeat store instruction. What this repeat store does, it starts with the address at EDI, keeps on moving the value in EAX for ECX number of times. So it is like a repeat loop. It is an instruction which does a repeat loop, but it is implemented in the hardware. So it does much faster than if you had written this as a kind of a repeat construct, repeat code in the assembly. Right? So the three things, you have to fill up all these bytes with the fill pattern. So you need the start address, which is at ETI. You need to know how many times you do it, which is 228 by 4. And this is the pattern that you fill with. So this whole space gets filled up with CCs. Right? So that's a basic fill value initialization, which is done. Let's go to the next slide. Next slide mostly is not further interesting in 31. Then you have A assigned 2, which happens in the same way. You have 3 assigned to B, which also happens in the same way. Then you push your parameters, which happens in the same way. From right to left, push B, push A through this, and then you call add. We'll see what happens as you get into add. But once you return from add, you had done 2 pushes. So you again do a pop, equivalent of 2 pops by adding 8 to ESP. And EAX again has the return value. So you move that to C and you are done. Then you have an AP lock, which is basically undoing what you had done at the Prolog startup. So you you set 0 to EAX, which we discussed yesterday. You pop the 3 registers that you had used for the repeat instruction. Then you release this space by adding 228 to ESP. And at this point, ESP and EBP must be equal. Right? And you run the check for that. Move EBP to ESP to make sure that they are equal. Pop the EBP because you have this is the base pointer of the caller of main, and you return from main. So this is the simple thing. We will come to the layout. I'm just trying to understand the code flow in this modified scenario. Okay. Now let us look at this activation record. So this is where you are. EBP is 1024, which is a control link, which stores the caller of main. EBP of the main, of the caller of main, CRT main. On the higher side, you have the return address and the 2 parameters. This, nothing has changed. Herein, if you see, underscore $A is -8. So your A is here, not at 1020, but it is at 1016. Then you have a jump of, a gap of 12 where you have B at 1004, a gap of 12 where you have 9C at 992, and then you have 4 bytes again, and then you have 192 bytes. This is the structure. So remember, I told that 228 is a magical number, which is 32, which is what you see here, 32 plus 4 plus 192. Right? This is the 228. Again, why we will see. So if you do this, and you have started by filling up this entire space by the fill pattern. Right? So when you are assigning 2 to A, that assignment happens at 1016 for a 4-byte pattern, because the integer is 4 bytes. So 1016, 17, 18, 19, over this you have written 2. Here at 1004 you have written 3. Here at 992 you have C. So you can see around every 4 bytes of the variable you have 2 other 4 bytes which are filled up with the fill pattern. Okay. So the reason you do this is this is for your debugging purpose. So what happens when you are running on the debugger? One thing I said that the fill pattern helps you to detect if you have initialized something or not. For example, if a variable has not been assigned, if A were not assigned. It would show like 0x, CC, all this, the entire thing. And then at that point, if you're trying to use A, read A in some instruction, say you are saying B assigned A, then the debugger would easily see that you have this pattern. And the debugger will give you a warning that, well, you are doing an uninitialized read, right? So that's the basic advantage. Now we are using this for a different reason. Now suppose you set a pointer to 1016, pointer P. Now, if your pointer is arithmetic, has something wrong, then you will happen to either read 1012 or read 1020 instead of 1016. Right? The moment you try to access that, the debugger would get to know that this is not something that you should be accessing, because this is in the physical space of the activation record, but not in the logical space of the computing program. Computing program should have addresses 1016, 1004, and 992, not this. And the reason you use particularly CC is the fact that CC happens to be the binary code for int3 interrupt. It's a software interrupt. So what it does, what the debugger does, it's when you access that, it checks on, and it basically uses this value CC for raising a software interrupt that says that you have done an address violation. Right. So it's a, I mean, I'm just trying to give you some scheme. It's not the actual compiler does, and that's how the debugger gets to detect such things in a very efficient manner. The debugger could have detected it by keeping a copy of the symbol table and calculating all that and all those, but that would have meant that after every instruction of the program, you would have 10 instructions of the debugger. Right? You still have some instructions of the debugger after every instruction, but at least you are trying to make use of some hardware features to make this firing of the software interrupts easier. So this is a local data with buffer, which is used in some compilers. This I'm showing is from Visual Studio, Visual C++, to make sure that you are not overrunning on memory. So naturally, you have three variables. Three variables have 12 bytes. 3 times 4, 12 bytes. And for every variable, you have 8 bytes of extra on two sides. So you need 24 bytes extra. So 12 plus 24 is a value 36, of which 32 comes directly in this computation. And the other side, 4 bytes of C, is the 4 bytes that you put here. So this layout will give you the 36 bytes instead of 12 bytes that you would have got if you are not doing this debugging. This 192 bytes is something idiosyncratic about the particular compiler. This is a buffer for edit and continue feature of the debugger of this particular compiler, which means that you are keeping 192 bytes available in the activation record, where at the execution time, while you're running the program, you can create and store a variable temporarily and make its use. Normally, you cannot do that, right? I mean, you need to recompile the program. The moment you recompile the program, you have a different activation record. But this debugger allows you to, from the debugger interface itself, to set some variables and their values without recompiling while the code is running. So where do you keep that variable? So for that, this space is allocated, and this compiler uses 192 bytes for that. This is idiosyncratic about it. If If you put off the edit and continue feature in compilation, these 192 bytes will simply disappear. And finally, you have, so this is the space that main takes, and for the activation record. And then on top of that, the 3 pushes that you have done, they will be staying. So your activation record of add will start on top of this. Okay? I hope this is understood. Let us go to the add function. In the add function now, you will have the same thing. So you have this coming at, there is this coming at 12, this at 8. So these are the 2 parameters, no change in that. And this comes at -8, as you have seen, because with that kind of buffers around the variable. Everything else is same. Here the magical number is 204 because it's 8 here. 8 plus 4, 12 goes for Z, and 192, that gives you 204. Use the same scheme of filling up this entire 204 bytes, that is 51 times 204 by 4, with this fill pattern. A simple thing. Next slide, slide 34. You are taking XY into EAX, adding it there, putting EAX to Z, putting Z to EAX. Now nothing, no changes. So before you return, you have to pop the 3 registers that you had saved here. Restore the ESP and then pop EBP, that is the base pointer for the main, which is, and the return value goes to EAX. Slide 35, the activation record of add, which is actually simpler. You remember we had ended in 768, so that is where the EBP of main will be stored, and then you have on this side Z, the 192 bytes, the 3 registers which you have saved here. Okay? So this is the activation record of add. I'm not walking through the code anymore because the code is walkthrough is a similar. Only thing, the address computations will be different in this case. So let me stop here, and before I continue to the next section, and see if there is any question. Is it clear how the debugging information is maintained? No questions. Okay, let me go back. These things are easy. You just have to learn the technique of decoding the assembly. So before I end, I will just take you through the handling of I/O, input-output functions, and handling of the optimized bit. So we again have the same function, same pair of functions, but earlier we were defining the values of A and B in main itself. Now instead we are reading them from the input stdin. So scanf %d %d ampersand a ampersand b. We are reading those values into A, adding them by the calling the function add and printing it. So it needs to have a interface with the input output function. So this will also help you to see how typically the library functions are handled at the assembly call level. And we will first go with a debug build. So I'm doing a debug build. These are 2 parameters, the Z, and I'm not using the local buffering. So in terms of add, there is no change. Now let us look at main. So I have the layout. Let's see. The size is 28. And here, like earlier, we had seen repeat for 228 or 204. Here it is just, 7 move instructions are generated one after the other, because the compiler must have figured out that when you are doing it 57 times or 51 times, it is beneficial to do that repeat instruction. But when you have to do it for 7 times, maybe doing the instruction execution 7 instructor is more more optimized. So that's a cost that it computes. Up to this point, now you have the scanf. So what you do is you are moving ESP to ESI. Okay. Then what you have to pass to scanf for B, you have to pass ampersand B, that is the address of B. Right. So when I write this address expression, again, what I mean is basically the value stored at that address. So what I'll have to do is not the value, but take the address itself. So we have already seen LEA does that job. So we will do this address expression and treat it as an address value, load effective address EAX. So EAX gets, say, pointed to B. Now, then address of B is passed by pushing. Then take the address of A, LEA again, address of A is passed by pushing. Then you push offset this, right? So you are pushing the parameters from right to left, right? So first you put the parameter ampersand B, then the actual parameter ampersand A, and then what you need to push? You need to push the string, right? So instead of pushing that string, you are pushing an offset here with the dollar value, which means that this string, as I said, that this is a string constant. So this will be created, this will be stored in the constant area, right? Constant memory segment. So in that memory segment, again, there'll be several constants coming one after the other. So, but since it's a constant memory segment, the system already knows where it occurs. Unlike the stack where it keeps on changing. But here you know, so all that you need to specify this format string is the offset in that constant segment where this string is stored. Right? So this is that offset value which you take and put that from the offset. You compute this and push that address. And then you make a call to scanf. You have already said at the beginning of the program, if you go to the left column at the top, after public main, you had said that these are the external symbols. That is import of printf, which is a procedure, import of scanf, which is a procedure, then other check routines, runtime check routines. So now you are calling that. So this will get linked with this extern imp scanf, imported scanf, and we'll call that as the call returns. You had pushed 3 parameters, the address of B, address of A, and the address of the format string. So 12 bytes. So you add that 12 bytes onto ESP. So effectively they are popped. And then you do the typical rest of it is again the same, calling add, which we have seen. You have to push B, A, and then call add. Rest of it, there is no difference. So this is what I wanted to show you. What is the typical way a IO function will be called? And there are 2 things, a couple of things to note here. First of all, this is a library function. So you do not have the function body here. You are handling it separately. Second, it shows you how string constants kind of are typically handled in the compiler at the activation record level. The fact that they don't go into the activation record because they're constants. They come from the constant area. And the third, this shows you, which is not very explicit here. It will be explicit if we look at the code of scanf, is the fact that this is a variadic function, in the sense that unlike add, which has two parameters, and it will always have two parameters, that's how you have defined it. Scanf may have one or any more number of parameters. One is minimum required, that is the format string. But then how many parameters you will have is not known a priori, it's not defined a priori. So the scanf, if you look at the assembly code of scanf, you will see how this kind of situations are to be handled, how you can handle, C++ kind of languages handle these variadic functions. And obviously, these all are in stack. So the basic issue that you will have, and now you can see why the parameter here is processed from right, is the only way you can know that there are two parameters is by decoding this format string, right? Otherwise, there may be as many parameters, right? So if you think about getting into scanf, as to how scanf will process it, if you would have processed the parameters from left to right, then this format string would have been deep into the stack. On top of that, you had A, on top of that, you had B. So you have to take out B, take out A, and then get the format string, right? But how do you know that there are two parameters? You don't. So how do you know that you have to take out two pointers, and then the third pointer is basically the format string? You do not know that, right? So you process it from right to left, which gives you the advantage that your last push was the format string. So when you get the control in scanf, you get this at the top of the stack. So the scanf knows that the format string is at the top of the stack. It takes out the format string, starts decoding. It knows that that is the next parameter, right? So it keeps on popping from the stack, and therefore, and there's hardly any check on that. So therefore, if you have a mismatch between the format string specification of number of parameters and the actual number of parameters given in that function, then often you get a runtime error. You won't get a compile time error because it is not decidable at compile time. So often you will get a runtime error because either you have not consumed some parameter which you were given, so the stack mismatches, or you have taken more parameters out than what was actually required, right? So, and this is at least one reason as to why you need this kind of, after having done this, before proceeding to call add, you are doing a RTC check ESP, runtime check for ESP, the stack pointer. Why are you doing this? Because you have to make sure that what scanf has done internally, being a variadic function, has actually adjusted the stack in the right way. Otherwise, what you get back at ESP here, when you are adding 12, expecting that you are just about to annul the three address parameters that you had pushed in, will be wrong. So this will get caught if scanf does some mess up, because you have not matched the format string specification and the number of parameters. Then this runtime check will catch that and throw a software interrupt, through which you will be able to know it, and the debugger will not proceed further. Right. So this is some insights into what happens in case of I'm just talking it in terms of IO function, but because what you get from the library by default are the IO functions which are variating. But I wanted to show you the handling of the IO, handling of the library function, as well as the idiosyncrasy of the variadic function, which all are issues at the runtime that you'll have to handle. Let us go to the next slide, slide 43. The call to add is done. the value of C has been obtained, which is in the EAX. And now you have to do this print, and it does the same thing. So it pushes ECX, where you have put the value of C by move, and pushes it on the stack, that is the rightmost parameter, and then it pushes the format string, because printf also has the same issue. For printf, the parameter type interpretations are different, because now printf expects a value, not an address. But the mechanism of variadic handling is the same. So this %d will tell printf will take out the format string first, and then by reading it is %d, it will know that there is one parameter, take it out, take it as C, print it, and do that. You come back, adjust the stack, and again do a runtime check for the stack pointer. And then you have the all your AP log to close. You close, adjust on the EBP, and these are different error conditions which are handled. We are not getting into that runtime errors much, but depending on the error, certain of these points will be raised. Certain interrupts will be raised. So now, this is what we saw in the debug build. So now let us try to do a release build that we will not have so much of debug information. The same code. Let us see what happens. Now, in terms of add, if you do, you know that the parameters are coming in from X and Y. So we are assuming you will remember that X and Y were pushed by putting the values in the ECX and EAX. EAX first and then ECX, right to left. Right? So when you call add, at that point, these registers also have the values that the parameter says. So the release build, it makes that assumption. So it does not allocate space for X or Y. It assumes that, well, they are there in the two registers. So it takes them from the two registers, adds ECX to AX. So there is no movement from X to AX or Y to ECX, because you know they're already there. That's the release optimization. And then you are moving that AX to Z. And then for return, you are moving Z to AX. Both of these cancel out because it's already in AX. So you just return. So this entire code reduces to just a single assembly instruction. Optimized. Release optimized. Now, why it is not a debug build? Because you won't be able to debug this code. You won't be able to set a breakpoint at Z assigned X plus Y and check the value of Z, because there is no Z. This activation record has no Z. The activation record has no X. You know? So naturally the result is reduction in both in terms of compactness of the activation record and the compactness of the code, or the reduction in terms of the code that you execute, both in terms of actual computation and in terms of, if you have noticed by now, that in the generated code for the management of the activation record, lot of the instructions that you execute are not the computation that you wanted, not X plus Y assigned Z, but the address arithmetic, the putting the value from register to the activation record allocation, putting it back, all these are taking time. So if you can, in the release build, you try to optimize, minimize those in terms of making the code efficient. Let us see what happens in main. In terms of main, you have A, B. You cannot optimize them out because you have a scanf on them. So you don't know, you cannot, you'll have to do the scanf and get the value. This is a call to scanf. Right? But all those, initialization of putting the fill pattern and all that are eliminated, because you don't need any of that, because you are not trying to debug. And then you do the call, then you come to add, you put these two in EDX and add it to EDX. Oh my God. Just see what is happening in the release. In add, we have already reduced it to a single instruction. But here, seeing that add is a single instruction addition, the compiler is deciding that the call to add is basically whatever registers we put it through. And those registers will get added. So why you put to those registers, push them, do the call and return? We can do that right in here. So the entire of call to add itself is optimized out. So you're moving A to EDX, adding B with EDX, and EDX is the result. Okay? All that you need after that is a print code from EDX to with the percentage, with the format string and so on. Right? So that is kind of the symptoms you will see when you do a release build. I will actually stop here. If you see in the presentation, we'll share it with you now. So I have worked out decoded assembly for variety of other features, like how typically double values are handled, how pointers, explicit pointers are handled, how struct, array, function pointer, nested blocks, all of these are handled. I'm not saying that you go and start reading them all, but as and when we make progress with the translation in the backend, these are very good examples to see how the activation record and the runtime handling typically can be done in a compiler. So I created, this is usually not available in textbooks. So I created this for the major features that C has. This does not have C++ examples like class and your, of course, namespace is lexical, class or member functions or stuff like that. But the major C features are decoded here for their runtime form. So let me stop here. If there are questions, then I can answer. Otherwise, I think with this, you will have a solid idea about how the memory is managed in terms of the activation record. And you will very soon get close to the point where you have to deal with the symbol table part of it. Like you are now on the LALR parsing. So right after this, you will go into intermediate code generation, where your interfacing with the symbol table will start in a heavy way. And then we'll go into the backend, where from symbol table to this activation record part will happen. But you have to keep this in mind that this is what you need to finally create at the runtime. So what will have to be there in terms of the address expression? So what will have to be there in terms of the symbol table? So what will have to come in from different constructs in the grammar, whether it is declarative constructs like int x, int a10, and so on, or it is executing constructs like a assigned b plus c. Right? So that's the whole continuity idea that we are trying to understand. So we are coming from two sides, so that on this side we are seeing absolutely at the end what is going to happen, and on this side we know the program and we're coming, and we will eventually meet at the point where symbol table will be holding the two sides together. Right? Okay.
Excuse me, sir.
Yes.
Sir, this is regarding the lab quiz that we'll have next week. So could you tell us the syllabus for the quiz?
Professor Mitra will tell you all that.
Okay, sir. Thank you, sir.
Okay. So, Praloy, are you there?
Yes, I am here.
Okay.
And
So-
sir, will the slides for module 6 be uploaded?
Yeah. Right now, I was not doing it because I was making. I mean, every time I make a presentation, I make some changes because
Yes, sir.
you all like the initial slides were not there. but you all raised those questions, so I thought yes, should be there. So it is final now. I'll just
Thank you
give
so
to
much,
Professor Mitra and he will upload it. Okay.
Thank you so much, sir.
Okay, welcome. So, Pralay, so what do you? I'm sorry, I took a lot more time than I had said.
No, it's fine.
An hour. I
Uh,
took an hour.
I think we can take a break of 5 minutes.
Yes, and then you
after
can
that
start.
one, I will discuss the assignment 3. And regarding the syllabus for the lab quiz that you mentioned, so it will be assignment 1, 2, and the lexical analyzer that we have discussed in the theory class.
All
That's
right,
next
sir.
one.
Got it.
Okay.
Okay, then. Thank you.
So we will start after 5 minutes.
Excuse me, sir.
Yes.
The
To me,
format would be the format for the quiz would be MCQs, or there will be a coding part as well.
So, Sadvik, let him start after 5 minutes break. So everybody is taking break. So after 5 minutes, you ask it again.
Good afternoon. So do you able to see my screen?
Yes, sir.
Okay, thank you. So first, before I start assignment 3, so probably you have few questions. So please let me know.
Okay. Sir, I have a few questions.
Hmm.
So what would be the format for the both lab and theory test, like MCQs or written or coding? What would?
No, actually, it will be a combination of all. So MCQ, MSQ, as well as some short answer type.
Okay.
Because we understand one thing, that if everything is in written, then based upon the typing speed, so it may affect.
Okay.
So it will combine all. Okay.
Got it. So this is for the lab, right?
For both test as well as lab.
Okay. So theory also might contain a coding part.
So in theory, what do you mean by coding? As of now, whatever we have discussed, there is no coding.
Like coding in the sense like typing some in the code, maybe commenting nothing.
Typing you have to do. Typing you have to do. So you cannot get rid of the typing.
Okay.
That you have to do. But yes, those things we will keep in our mind, that say the test will be for 1 hour, each test, class test 1 and the lab quiz 1. So the typing time will be enough for the test, as well as the thinking time. And say for whenever it is say MCQ or MSQ, then you have to do some sort of calculations. So please keep your pen and paper handy and ready. So probably you have to do some calculation or something you have to perform, and after that one you have to answer that question, even if it is MCQ.
Got it. And the platform would be Moodle, right?
Anything else regarding the syllabus? I think it's clear. So as we mentioned that for class test it will be up to the parsing, and for the lab quiz it will be assignment 1 and 2 along with the flex. The assignment 3 will be on flex, that we are going to publish assign today. But you know, the theory we already have discussed on the last week and before that one. So I think that's fine, and that will also be included in the lab quiz 1.
So I have a doubt in assignment 2 as well.
Okay, tell me.
So in assignment 2, like while reading the float number and printing it, the exact value of float is in printing. Like for example, if I'm giving an input of 100.235, so like the number that is being stored is like 100.23498.7, like that.
No, I got your point. So actually, some of you already has sent an email, and all those who sent an email, so I replied to them also. Okay. So the point is, so that is kind of a numerical approximation error, which also happens if it is not your function. If it is a C function, then also it may happen. Okay. So those cases we will consider, but it should not be the situation that when it is very straightforward, then also you are making some mistake. It should not be like that.
Okay.
So the approximation you are talking about doesn't occur always. Probably you noted that one when say you are printing or doing something, isn't it?
Okay. Yeah, got it. And sir, like I created a test case in which there was like 6-7 digits in the before the decimal point and 3-4 digits after the decimal point for the floating point number.
No,
Hello?
that is fine. But
So-
regarding this floating point number, I also mentioned. So whoever asked to them, I mentioned that look, floating point number you can represent in 2 different ways. So having a decimal point, and then there is an integral part and fractional part that way. And also you can represent in IEEE 754 format, where there is a mantissa and exponent. Now, if you use mantissa and exponent, then your range will increase.
Yeah, I got it. No. I wanted to ask like that if there are like 6 to like the number is 1212.123. So like what my program was printing was 121212. The before the decimal part, the integral part was correct. Then after.
I understand your point, Satvik, but the situation is that along with the test case what you are supplying or you tested on, apart from that one, the TS will have a set of tester. Sometimes we will provide some tested data. So your program or your assignment should be generic enough so that it can support all those test sets. Unless otherwise, it's a very corner cases. Okay, say for example, say if I ask you print 22/7, then definitely based upon how many digits you are printing, the value will vary. So those kind of things are corner cases. But apart from that one, there should not be any straightforward case and your method is failing. It should not be like that.
Sir, are we taking input like 22/7, like the slash one as well?
No. I am just giving an example of storing that data. So if you store that data, okay.
Got it. So we are taking input the decimal point one and the enter right?
Yes. It is just look, the internal division, multiplication, all those arithmetic operations will be performed inside your program. So as of now in assignment 2, whatever we have done, reading and printing. So just bypassing stdio.h or IO stream, we are having our own library function. That's it.
Got it. Okay, sir.
Sir, so one thing.
Yes, Vineet, do you have any question?
Yes, for the floating points, will the inputs contain that exponent?
Give me a minute. Please give me a minute. There is some background noise from my fan. Okay, now tell me.
So for the floating points, you also have to consider the inputs with the E notation, means 1.1 E10 like that.
Right. Yes. Okay. Scientific representation also you need to consider.
Okay.
And sir, while printing, so let's say I input I input 1E10 for example. So then while printing, will it print? Are we supposed to print in the decimal notation itself, or like?
Look, as of now, we didn't mention any restriction on that one. But as you understand that when say the number is very large, okay, say if this number is say 10 to the power 20, that kind of number.
Yes, sir.
Then
are we supposed to support that kind of large numbers for float?
I believe there is no problem in implementing that one from your side, is it? So you will be storing say mantissa and the exponent part, and that way you can store and support any numbers. Don't be scared. If you write it correctly, then probably without your knowledge, your program is capable of doing this one or handling this one. Only thing is that when it is outputting, so during that output, so it's not a convenient way that say if the total number of characters which are being printed is say more than say 20 or 30. So you will also agree with me that when I print something like that on the terminal, then so nobody will appreciate that one. So instead of that one, so why don't you compress based upon that the value of the floating point number? Why don't you during the runtime you decide that in which representation you should go and present that way? That is my point.
So in the assignment, things are you specified that we have to match the scanf %f format, right?
Yes, sir.
So that is
yes,
enough,
sir,
right?
exactly.
So if you match that, it's okay, right? Because you said we just match the scanf, whatever scanf does. Say printf.
Right.
Okay. So that's
so if it's a float, then we cannot exceed the boundations of a float because we are storing the final value in a float only.
Yes, but my point is, look, so if you write the function in a generic way, then it can able to support. So there is no need to worry.
It is able to support, but the final output is being stored in a float. Like if you're saying like 1e part 20, then this is something which is beyond the range of float.
No. If it is beyond the range of the float, if it is say overflow or underflow case, then definitely it will not support. That you need to mention. So similar to that one, so when the situation will arise that you are trying to print something where there is a division by 0 or the value doesn't exist, so any n kind of thing, so that you have to report. So there is an option that you can print success or error. That option is also there.
No, but like there wasn't any option to print like these statements. Like we have to return the.
Look, the point is that if you implement to perform some basic value printing and scanning, that is fine. But if you go for a more generic version, then you have to think about every corner cases. Okay. Now we are not pressing you or making it mandatory that you consider all those corner cases. But if you have done it, then it is good actually.
Okay, got it. Fine.
That is the reason when, so you asked, some of you already asked me the question over the email. I replied only. So it is not the case that I reply to all and making that as a constant for everybody. Okay. But always there is a scope of improvement, and if you improve, then it's a good thing. So you will see that, yeah, your program is doing good, and it is at par with, say, scanf or printf of the current stdio.h or IO stream. Okay, anything else? Okay, so before I go to that assignment 3, I believe that you are aware about the fact that next week there will be tests, but the classes will also be there. So as per the academic section, so we will have the class on Monday and Tuesday as usual. Only thing is that Thursday, instead of the lab, there will be test. So we will start at 2. I will send an email also to all of you. We will start at 2. So say class test will be there. After that, we will take a break of half an hour. Then lab quiz for 1 hour will be there. So like that way it will be. Okay. But Monday and Tuesday classes will be there. Okay. Now I'm going to assignment 3. This assignment is designing the Lexar for TinyC. So let me first explain what is TinyC. So we are trying to write a compiler. Now regarding the language, we are considering the C language, but the support for the C language is huge. So we are restricting ourselves to a subset of the C languages, and that subset we are calling as the TinyC. That's why it is TinyC. So assignment 3, 4, 5, 6, whenever you will see, so assignment 3 is on Lexar, assignment 4 will come for parser, after that IR generation, then target code generation. So everything will be done on TinyC. So this is the name we are calling that TinyC. It is the subset of the functionality of the C programming language. Okay. So today it is being assigned, and the submission deadline is September 15th. So about 2 weeks from now. And given the content, you will see that one. You will understand that it's possible. So within 2 weeks, definitely possible. So I think that later assignments may take some time, but this actually is for 1 week. But since next week you have a test, so we give a relaxation, and 2 weeks are given. And one good news is that assignment 3 onwards, it's a group assignment. The group information I uploaded in Moodle. So please check that one under assignment 3. So I believe that all your concerns has been addressed. Still, if you find that there is some mismatch, so please let us know. And also one request to all of you, I found that about 8 to 10 students didn't update their roll number in the Moodle. Actually, I know that in the Moodle there is no field like roll number, but I insist to fill your roll number in the ID, so that whenever say we will evaluate or say we will download the marks from the Moodle, then it will be easy for us to map you with the ERP data. Okay. Now for this, full marks is 100. The assignment follows the lexical specification of C language from the international standard ISO IEC 9899-199E. So this particular file is also uploaded in Moodle. So last time I missed it, so this time I didn't make that mistake. I already make it available in the Moodle. So if you want, you can download from this assignment file also from the Moodle, and you can look at it in your terminal. It's up to you. But you have to follow by my cursor. Okay. So to keep the assignment within our required scope, we have chosen a subset of the specification as given below. We shall refer to this language as TinyC, as I mentioned. And shortly you will see, so this is Lexar or scanning process. So the tokens or the sequence of the characters or the patterns that we are going to support is the subset of the C program. But we will see that most of them are being covered here. So we are mostly covering them. And subsequently, in a later assignment, specify its grammar from the phrase structure grammar given in the C standard. The lexical specification quoted here is written using a precise yet compact notation typically used for writing language specifications. We first outline the notation and then present the lexical grammar that we shall work with. Okay. Now the notation, in the syntax notation used here, syntactic categories, non-terminals, are indicated by italic type, and literal words and character set members, which are terminals, by bold type. A colon following a non-terminal introduces its definition. So what is their pattern? That information is being introduced here. Alternative definitions are listed on separate lines, except when prefaced by the words one of. An optional symbol is indicated by the subscript of. I will show you that, so that the following indicates an optional expression enclosed in braces. So when this is written, say expression with a subscript OPT, then expression in italics indicates that expression is non-terminal, and in the subscript OPT indicates that this expression is optional, which means it may or may not happen. Okay. Now in the lexical grammar of TinyC, the tokens are of either of the 5 categories. It can be keyword, it can be identifier, it can be constant, it can be string literal, it can be punctuators. So these are the tokens. You remember, tokens means a sequence of the characters following a particular pattern. So when I say token keyword, then keyword has a pattern. Identifier has a pattern. Constant has a pattern. String literal has a pattern. So all those patterns I have to list, or I have to define against them. And as per my convention, this non-terminal, so they are italics, so they are actually non-terminals: keyword, identifier, constant, string literal, and punctuator. And also, as per my definition, when after keyword I will give a colon, that means I am defining the pattern for keyword. Here it is. You are familiar with this from your programming and data structure class. Keyword will be one of, say, auto, enum, restrict, unsigned, break, extern, return, void, case, float, sort, volatile, character, for, sign, while, constant, goto, size of, underscore bool, there is an underscore, bool B is capital, continue, if, static, underscore complex, default, inline, struct, underscore imaginary, do, int, switch, double, long, typedef, else, register, union. Now you please note, we also discussed that all these keywords has the capability to act as an identifier as per the rule of the identifier. The rule for the identifier we will discuss later, but you remember that in the lex file or flex file, we mentioned that if we define keyword first, then when it will be auto, then it will be mapped as a keyword. But if we define identifier first, then auto may be considered, since the pattern of the auto also matches with the pattern of the identifier, will be considered as an identifier. Okay. Now regarding all the keywords, specifically you have to write them. Otherwise, you know that you didn't find any pattern that in sort you can write that one. So you have to explicitly write those things as keyword, but the choice is you have to write in the flex format in such a way that only one of them will be picked at a time. Okay. Now regarding the identifier, the definition identifier is non-terminal, colon indicates the definition of identifier. So it will be identifier non-digit. What is identifier non-digit will come later, but from this name also you can understand that there should not be any digit. And that is the rule for the identifier, that it should not start with any digit. Followed by identifier, so recursively it is occurring, so any number of times it can be identifier non-digit, and after that it can be identifier any number of time it can be identifier, which includes identifier non-digit and identifier digit also, and finally it will be identifier non-digit. Now if you look at these two, identifier followed by identifier non-digit and identifier followed by digit, it indicates that it will start with identifier non-digit, then any number of identifier non-digit or digit, and it will end with identifier non-digit or digit, and you know that that is allowed. Okay. Now what is identifier non-digit? A to Z in small and capital is considered as identifier non-digit along with underscore. At the very beginning it is underscore. So for all those students who has a tendency of copy paste, please note it that underscore may not be copied correctly and pasted in your source text editor. So be careful about that one, otherwise you may miss this particular character underscore. Okay, again it is one of, so one of will be selected there. Now you understand from here also that if you are willing to make your program case sensitive, then this is the place where you can mention them. Since A to Z all are different, so it will be case sensitive. Okay. Now digit one of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 all can be, and that way your identifier definition is complete. Next is constants. As you know, constant is of several kinds. So constant, this is non-terminal. This colon indicates definition will follow. Integer constant it can be, floating point constant it can be, enumeration constant, what it will, I will come to that, and character constant. So integer, floating and character we are mostly aware of. Now enumeration constant is also there. Now integer constant means what? It should not start with 0. So it will start with non-zero digit, and then any number of integer constant, recursively it is calling, and digit will be there. Non-zero digit means one of 1 through 9 except 0. This is to avoid the leading zeros from your integer constant, or even for the floating number also. You do not expect that it will start with 0. Floating constant is fractional constant, exponent part. Now here you see that subscript, it is OPT optional. So in a floating constant, it can be only fractional constant, exponent part may be optional. Else digit sequence followed by exponent part can also be there. Okay. Now in the fractional constant, digit sequence optional dot digit sequence. This can be one situation. Another situation, digit sequence dot nothing is there. So here you see one dot is given. That dot, if you look carefully, you will see that is bold, which means that is a terminal one. So that is a single character. Now in the exponent part, it can be either small e or capital E. Sign is optional. Sign is one of plus or minus, and then digit sequence. Sign is optional in the sense for the positive, we may not want the sign. Okay. Now in the digit sequence, digit followed by digit sequence and digit, it will be there. Now enumeration constant is identifier, character constant, everything inside the single quote. Again you see that this single quote is bold, indicating that it is a terminal symbol and it is the single character. Inside the single quote, it is C-char sequence. What is C-char sequence? It is C-char and C-char sequence recursion C-char. And what is C-char? Any member of the source character set except the single quote, because single quote is already considered as the quote inside which it will occur, backslash or new line character. Escape sequence one of slash quote slash double quote slash question mark double slash slash a slash b slash f slash n slash r slash t slash b. Okay, now I am coming back to this point of integer constant and floating point constant. Now if you look at this integer and floating point constant, then it says non-zero digit followed by integer constant and digit. So here in this tiny C compiler, we are ruling out the situation that when it will be an integer, then it will be represented by scientific representation like E, exponential of. We are ruling out that possibility in this tiny C version. So that's why I mentioned, yes, if you want and if you make it more powerful, then you can include in your printf that for large integer number you can add E, but it is not mandatory. Why I am telling that it is not mandatory? The reason is here. Now for the floating point constant, so definitely I agree that whatever may be the representation, then there is a possibility of overflow and underflow, both for the floating point constant. So those cases must be reported as an error cases, but that I cannot represent, because it is always whatever may be your array, then it is always a finite one, and with that finite array I cannot guarantee that it can support -infinity to +infinity. But the point is, when it is floating point constant, it should support two situations. One is the decimal point is present and there is an integral part and there is a fractional part. Integral part may be optional, fractional part can also be optional. Another situation, here the exponent will be present for the floating constant. So if you have support for this integer and fractional constant, then you are good, because at the end of this semester, when you are done with this, say starting from the lexical analyzer, parsar, then code generation, etc., then you have to call your own library function in order to print your number. And since you are supporting integer constant and floating point constant like this, then if your library function supports only this, then that is fine, absolutely fine, no problem. Okay. Now in the string literals, you know that it is double quote. This double quote again is given as bold, indicating that it is terminal and single character. Inside is character sequence OPT optional. This optional will allow you to have one situation where the string is null. There is only /0, nothing else. That will happen when you will give just two double quote, indicating that there is nothing null string kind of thing, only /0 is there. So it gives that opportunity or possibility, followed by a-char sequence, a-char sequence and a-char. So recursively it is calling a-char sequence and then a-char itself. Now a-char is what? Any member of the source character set except the double quote, which is already there here, backslash or new line character. And it can be escape sequence also. The list of the escape sequence is given above at the point 4 when I was discussing this constant. Okay, so escape sequence is given like this. So all these escape sequences can be part of this string literal. Okay. Now the final one token is the punctuators. Punctuators, you know, is one of these which are given here. So these will be considered as punctuator. Now you remember in one of the initial classes we discussed that say there is a possibility it will be only single less than or double less than, and whether it is a single less than or double less than, based upon that one, its interpretation will vary. Now you see that when I am calling this punctuator as a token, then there are two possibilities. If I get less than, then that is one punctuator or one token. If I get double less than without any space in between, then I will get another token which has a separate meaning. The meaning will be added later. Additionally, we have to handle comments. As you know, in C, there are two ways to write the comment. One is multi-line comment, which is inside slash star star slash. Another single line comment, double slash. Now this single line comment or double slash indicates that anything and everything after this double slash until you encounter one new line is part of that comment. And for multi-line comment, this slash star will include all those things inside this one until you will reach to slash star slash. Everything including the slash n is also part of this comment. So except within a character constant, a string literal or a comment, the character slash star introduce a comment. The contents of such a comment are examined only to identify multi-byte characters and to find the character star slash that terminate it. So thus within these comments do not nest. That is my assumption. So if the situation is they are nesting in nature in the multi-line comment, then I cannot able to support. That is my declaration or assumption in this case. Okay. For single line comment also, I will do that one. Now you know these comments are for the programmer. It has nothing to do with the compiler. So those will be removed and those will not be considered as a token. And that is not also required to the parsing stage. Okay. Now in the assignment, you have to write a specification for the language of TinyC. What is TinyC? Whatever we have defined here as token. So these are my lexical elements. So this you have to code in a flex program. Okay. Using the above lexical grammar, name of your file should be ass3_role.l. The ss3_role.l should not contain the function main. Write main separately as ass3_role.c. Prepare a makefile. By this time, I believe you know how to prepare the makefile to compile the specification and generate the lecture. You will see that this will be real fun that you write one makefile. Now you are writing ass3_role.l. In the next assignment, you will write ass3_role.y. That will be your Bison program. And regarding that, required changes will be done in your makefile. And that way, if you keep on adding more and more files, then you will see that it is evolving and finally you will have one compiler with you. Prepare a test input file also and give a name like ass3_role_test.c that will test all the lexical rules that you have coded. And finally, you tar archive and use this file name and upload in Moodle. So the marks division is like this. For text specification, it's 60. For main function and makefile, 15 plus 5, total 20. For test file, it is 20. Okay. Now, if you have any question, please let me know.
Sir, isn't this a group project?
Yes, yes.
So, sir, whose roll number do we put?
Oh, okay. That is a very good question. So it doesn't matter. You can put your roll number or your partner's roll number, and we request you to go for only one upload. So it is not required that you and your partner both will upload. So since it's a group project, so only one upload is enough. And we also request that you go for the one upload. Yes, that is a good question. Now, Okay, if you want your roll number also, then you can put 2 roll numbers concatenated. Okay, partner 1 and partner 2. That is also fine. But I request you to upload using only one login. Okay, you can put okay, I can modify. You can put roll 1 and roll 2, your partner roll number and your roll number. That's fine. And also that will be that will be good for us also, that we can quickly cross check that whether the group table is matching with this or not. So so all of you, did you check the group information which is available in the Moodle?
Yes, sir.
Moodle? Okay. Okay, that's good. And you can able to access the assignment 3 also, right? It's visible.
Yes, sir.
Okay. So any other question?
So what do we have to do inside the main?
So from the inside the main, you have to call that lexical analyzer. So
in the assignment it's written like inside the main we have to test the lexer and we have to make a separate testing file as well.
Yes.
So like
the testing file, look, testing file will contain the source code following the TinyC, and main function will call the lexer, and then it will basically, or in the main function also, what you can do, I believe that you have done command line programming also. In the main function, you can have that the main function will consider the source code as argument 1, argv1. You will consider that as an argv1. Then what will happen? The way you compile your source code, you write gcc hello.c. Now you will write /a.out, then say my source.c. Then it will compile, and then the lexical analysis is done. It will output the list of tokens. Okay. Is that point clear?
So is starring the file compulsory, or we can zip it as well?
Oh, that you can zip it as, no problem. No problem. I think that is the easy question to me. Okay. So if there is no more question, then we can